Well, we've talked about continuity. We've also talked about finding a derivative. Differentiability is the ability to take a derivative. Okay, so I think it's worth just go ahead and saying that right now. Differentiability is the ability to determine slope at a point. Okay? That's a very rough definition that I just kind of made up, but it is true. It may not be the textbook definition with all the notation, but it's there. All right, the derivative of f at x equals c is, okay, now this is the alternative form of a derivative, an alternate form. And what you have already encountered is this right here. So we have the derivative at any specific point. We've gone through some examples. But now we're going to have an alternate definition, another way of representing the same thing. So the slope of f at some x value c is the limit as x approaches c. X minus c is in the denominator. Okay, so let's pause right here. I would love to plug a c directly in the place of every x, but then I'd have c minus c. I'd have 0 in the denominator, right? And the numerator is f of x minus f of c. This is slope. Y2 minus y1 over x2 minus x1. That's what it is. That's really what it is, okay? And there's a little caveat to this. If this is going to be true, like if this is going to exist, if this limit exists, then we have to have the limit from the left, pause as I write it, match and equal the limit from the right. If this is going to exist, then this has to be true. Oops, I wrote does not equal. I meant to write equals. If this is true, then the derivative exists. At x equals c. Okay? All right, so let's do this. Let's determine the slope of the line tangent to that graph. Now, these are going to be worded differently, so we can get used to all the different phrasings. And here it is. We're going to use some of these little phrasings right here. Find the slope of the line tangent, find the value of the derivative, those kinds of things. So we want to find the slope of the line tangent to this graph at that point. So at x equals -1, which is right here. Let's use a pencil for just a moment. I want to know the slope at that specific point. Here's a tangent line. It's positive something. That was a very rough tangent line, very wide tangent line. But it's positive something. I don't know exactly what it is, but it's positive something. So let's switch to green. No reason, just for fun. I think, wasn't that fun? So the derivative at -1 is, okay, we're using the alternate form of the derivative, and this is a good way to check for continuity and differentiability. This is why we use this as opposed to the other one. So we need the limit as x approaches -1 of g of x minus g, I almost wrote the letter f, whoops, there we go, g of -1 over x minus -1. Okay, so let's go for the obvious. If I plugged a -1 in, substitute a -1 in for x, I would be dividing by 0. That's not going to work. But what I will do is proceed with this algebraic process. We have x plus 1 in the denominator. So I like to go for the low-hanging fruit first. If I plugged a -1 into the g function, we can look at the graph for this, I would have -3. So we're going to be subtracting a -3. And then we're going to have all the g stuff here. So 2x cubed minus x minus 2 minus -3. Okay? Let's continue simplifying some things. Again, totally wrong to plug a -1 in. We'd be dividing by 0. Not going to happen. We have the limit as x approaches -1. And we have 2x cubed minus x, let's see, plus 1. All divided by x plus 1. And I would love to factor that numerator, and it actually does factor, but it's this bizarre way of going about things that's the best way to do it is to grab a different color pen and do a little trick we call synthetic division. So, and here's why. When I'm dividing by a linear term, I can use synthetic division, particularly the easiest form of synthetic division, when I have a understood 1 in the front. So -1, and that comes from the opposite of this. And then my numerator holds all the coefficients that I need. So 2x cubed, 0x squared, minus 1x plus 1. There we go. This process should look familiar. It pops up again. Aren't you glad? Bring down your 2. -1 times 2 is -2. 0 times 0 plus -2 is -2. -1 times -2 is 2. -1 plus 2 is 1. -1 times 1 is -1. We add those, we get a 0. My remainder is 0, which means this truly does reduce, which is going to be very convenient. So the whole purpose of that was to reduce a fraction. This is how I reduced that. So here's what's about to happen. What I'm really finding is the limit as x approaches -1 of 2, -2, 1. Those are my coefficients for not something cubed anymore. We reduced it. 2x squared minus 2x plus 1. Okay, may I plug a -1 in now? Yes, I may. And I have 2 times -1 squared minus 2 times -1 plus 1. And that gives me 2 plus 2 plus 1, 5. The slope of this really awkward looking line that I drew that's supposed to be tangent at that point is 5. Okay, let's do the next one. And the next one's going to get a little bit tricky and a little bit crazy. But on this one, I didn't have to really talk about the slope from the left and the slope from the right because we had this continuous function that really met up here and flowed very well. Here we have a continuous function that meets up here, but it doesn't flow very well. And I want to know the slope at x equals 1. So I want to be able to draw a line tangent to this jagged function at this point. So now the question is, where do I draw this line? Do I draw the line consistent with this piece? If I drew a line, would I draw it here? Would I draw it here, kind of coming off the parabola? Would I balance the two? Like what would the tangent line look like? Can I even do it? Let's find out. So switching colors again. This is going to be a multicolored lesson. Let's go purple. Let's find the limit as x approaches 1 from the left. We have to go from the left and the right because we have two different functions, two different pieces of functions that meet at this one specific point. So I need to find the derivative and that's going to work only if these two different limits are equal, right? So we're going to go from the left, go from the right, see what happens. So we have -x squared plus 2. That's going to be this piece right here. I'm going to start going from the left. By the left, I mean less than 1. So that minus -1 squared plus 2. That is not -1 squared. That's -1 squared. Just to be clear, I'm squaring the 1 and then changing the sign. Let's put some parentheses around that. All that divided by x minus 1. Let's go ahead and simplify a whole lot of stuff. We're going to have the limit as x approaches 1 from the left. X minus 1 is in the denominator. By the way, I'm going to back up. I just feel like I went too fast. This is f minus f of 1. Now, you might say, well, f of 1 would take you here. I know. But when we do this, we are dealing only with stuff from the left and stuff from the right. So it's okay to plug a 1 in here in the process of figuring out this limit. Totally okay, because we want to know what we're approaching, not necessarily what we are. So we have -x squared. I'm going to do a lot right here in my head. All right, 1 squared is 1. That makes it -1. -1 plus 2 is 1. So I have 1. I am subtracting 1. And that gives me 2 minus 1. So plus 1. There we go. That's what we have. We're going to continue doing this. You might want to go synthetic on it. I'm actually not. I'm going to do some crazy factoring. And just to save space, I think I wrote this fraction bar a little too long. need to use some extra space over here. Limit as x approaches 1 from the left. There we go, x minus 1. And we're going to factor a negative 1 out. That gives me x squared minus 1. And we'll continue factoring. Am I going to have room? Afraid not, but I'm going to try. The limit as x approaches 1 from the left. Denominator is the easy one to write in this tiny space. Numerator is negative, and then x plus 1, x minus 1. Oh, is it going to work? Yes, I was able to squeeze it in. Yes, there we go. That says x plus 1, x minus 1 with a negative in the front. That's the negative we factored out. I'm going to grab a pencil and cancel these. And that's going to give me the limit as x approaches 1 from the left of negative x minus 1. Okay, so that's the negative x minus 1. I'm going to plug a 1 in. At this point, I get negative 2. Fantastic. We're halfway done. Actually, we're going to finish the next part of it very quickly. The next one's going to go a little bit quicker. So let me separate the work from finding the limit from the left from the work from when we find the limit from the right. Now, again, as we find the limit from the left and find the limit from the right, if they match up, then the derivative exists. Otherwise, the derivative will not exist, and we will say, well, you know what? The slope doesn't exist there. If that happens, we'll cry about it and talk about it in that order. We'll cry, then we'll talk. There we go. We're approaching 1 from the right. Now, when we approach 1 from the right, we're going to use this piece of the piecewise function. So negative 1/2 x plus 3/2 minus, and then we're going to plug a 1 in, and that gives me negative 1/2 times 1 plus 3/2. All that divided by x minus 1. Again, plugging in a 1 for x at this point is wrong. Let's keep working. The limit as x approaches 1 from the right of x minus 1 in the denominator, we have negative 1/2 x, and let's figure out the rest of this. We're going to have, let's see, negative 1/2 plus 3/2. That's going to give me 2/2. That's 1. So I have 3/2 minus 1. It's going to give me 1/2. So plus 1/2. Let's keep going. Let's bring it down here. Limit as x approaches 1. All right, purple pen, you better work with me now. Don't you go dying on me. Negative 1/2 x minus 1, and then x minus 1 there. Oh, my word, this purple pen is, come on, hang with me. You can finish this problem. Come on, you got this. I'm left with the limit as x approaches 1 from the right for negative 1/2, which is simply limit as x approaches 1 from the right of negative 1/2, which is negative 1/2. Come on, purple pen, come on. Ah, I'm giving the rush she's got, Captain. Have another purple pen somewhere. All right, anyway, I get negative 1/2. Here's the problem. We have quite the situation here, and here's the situation. We had a slope from the left that equaled negative 2, and a slope from the right that equaled negative 1/2, so therefore the value of the derivative does not exist. And I'm going to write that, not in purple, obviously, not that I'm bitter, but I'm going to write that. I'll write it in red. F prime of 1. The slope of this function at 1 is undefined. The limits, the limit itself coming from the left and the right, they don't match up. So we could say the limit doesn't exist. Therefore, the value of the derivative is undefined.